Hello friends, I welcome you in lecture number 2 on heat equation. In lecture number 1 we have discussed about heat equation, and in this lecture we are going to discuss solution of heat equation, and this is the first case. We have discussed two different cases for heat equation in our course, and those two cases differ with respect to the boundary conditions. So in first case we are going to solve the heat equation with the boundary conditions given by this equation number 2. That means value of temperature at end points of the given metal rod or metal bar is 0. We consider that at ends say A and B, suppose at this end value of x is 0, and suppose at this point value of x is L, then we assume that temperature is 0 at x equal to 0 and at x equal to L for all values of t. Here I will write for all values of t which are non-negative. So first we will solve this heat equation together with this type of boundary conditions, and this is the initial condition that u is given by some function of x at time t equal to 0. And in second case we will consider another type of boundary conditions which are del u by del x is 0 at x equal to 0 and del u by del x is 0 at x equal to L. This will be our second case for the solution of heat equation. First we are going to discuss the solution of heat equation in which boundary conditions are given by this equation number 2, that is temperature is 0 at both the ends of the bar or given metal rod. So to find out the solution of this equation number 1 together with this boundary and the initial condition, we are going to apply the method of separation of variables. So our aim here is to determine the temperature uxt at any position x and at any time t, and for that we assume that suppose this solution is written as product of two functions, one is function of x only and another is function of t only. This is the method of separation of variables. We always start by assuming that our solution is the product of two functions of given two variables. Here u is function of two independent variables x and t. So we assume that this function uxt is nothing but product of function of x only and function of t only. And I have written this solution systematically here that I will discuss here. So here this is the heat equation, and we are going to solve this one dimensional heat equation together with boundary conditions given by u0t equal to 0, ult equal to 0 and initial condition ux0 equal to fx. And we start by assuming that heat equation has solution of the form uxt equal to capital X into capital T, where x is a function of x ln and t is a function of t on ln. Now what is heat equation? Del u by del t equal to c square times del square u by del x square, and we have assumed that this is the solution of this equation. Therefore this equation number 5 must satisfy this heat equation. That means if we find out del u by del t from this and del square u by del x square from this equation, then that we can substitute here because 5 is the solution of this equation. So first I have to write down del u by del t and del u by del x from this expression. So here we can see del u by del t, that is partial derivative with respect to t. So we consider x as constant and derivative of capital T with respect to t, that we denote by t dash. So that I have written here, del u by del t equal to x times t dash. Similarly, if we differentiate this partially with respect to x, we consider t as constant. Derivative of x with respect to x is denoted by x dash. But we require second order partial derivative with respect to x. So we again differentiate this with respect to x, considering t as constant and derivative of x dash is x double dash. And then we substitute these two values, del square u by del x square and del u by del t, in this equation. So after substituting these two values in heat equation, we have this expression x times t dash equal to c square times second derivative with respect to x times t. And now we have separated the variables. We take this x on this side and c square times t in the denominator of t dash. And now we know that this left hand side is a function of x only, right hand side is a function of t only, and both are equal. So this can only be true if both sides are equal to this same constant denoted by small k. And if I compare these two, I will have x double dash equal to k times x, that I can rewrite as x double dash minus kx equal to 0. And by comparing these two, I will have t dash equal to c square k times t, that I can rewrite as t dash minus k c square t equal to 0. So now we can see we have two ordinary differential equations. This equation number 6 is second order ordinary differential equation in variable capital X and small x. X is a function of x. Similarly, this is ordinary differential equation in capital T and small t as independent variable. First we solve equation number 6. Before that, we know that boundary conditions are given by u0 t equal to 0 and ult equal to 0. But what is u? U is assumed as x into t, and here we are taking small x equal to 0. Therefore, if I substitute from this, I find out u0 t equal to x of 0 into t of t. So we take x equal to 0, small x equal to 0, and this is equal to 0. So now this is possible if either this is 0 or this is 0. But if t of t equal to 0 for all t, then u will become 0. And we are interested in the non-zero value of temperature. So we will consider x of 0 equal to 0. And if I use another boundary condition is u of L comma t equal to 0 for all t. And from this expression, u is given by x into t. So here small x is L, therefore x of L times t of t equal to 0 for all t, and therefore we must have x of L equal to 0, because if this is 0 then u is 0. So what we have obtained, that here this is second order ordinary differential equation and in variable capital X and small x, and we have two boundary conditions, x of 0 equal to 0 and x of L equal to 0, and we have to decide the solution of this equation number 6 which satisfy these two boundary conditions. So I have written all these things here, how we obtain these two boundary conditions for that ordinary differential equation which we have given number 6. Now to solve equation number 6, we can see it is linear ordinary differential equation with constant coefficients and it is homogeneous. So to solve equation number 6, I have to write down the auxiliary equation corresponding to this equation. For auxiliary equation, we replace nth derivative by some power of, say, variable m. Here I have second order derivative, so I will replace it by m square minus k. X means 0 derivative, that is m raised to 0, which is 1. So this is going to be auxiliary equation corresponding to equation number 6. And if I solve this, I will have m square equal to k. Therefore m equal to plus or minus k. And k is real constant, so we can see these roots are real and distinct. So that I have written here. Before going for this, I have to consider these three possibilities, that this k can take three different values. K can be 0, k can be positive, and k can be negative. So we will consider this auxiliary equation in these three different cases. So first I am considering that k equal to 0, and we are considering this solution for this equation number 6, x double dash minus kx equal to 0, and together with the conditions xl equal to x0 equal to 0. Now if k equal to 0, I will have x double dash equal to 0, and for x double dash equal to 0, auxiliary equation is m equal to 0. Therefore we have m equal to 0 repeated roots 2 times. That means I have x equal to some constant, say b into e raised to 0x plus some another constant into e raised to 0x. But e raised to 0x is repeated, so here I multiply by x, and e raised to 0x is 1. Therefore capital X is a into x plus b. This is general solution of this differential equation, d square x by dx square equal to 0. Now we can use these two conditions. Suppose I use this condition, x of 0 equal to 0. That means when small x is 0, capital X is also 0. So if I take x equal to 0 and this x equal to 0, I will have b equal to 0. For second condition, I have to take small x equal to capital L, capital X equal to 0. So that I have used here a into L plus b, but b is 0, therefore a is also 0. And hence we can put values of a and b here, and we obtain that capital X is identically 0, or value of capital X is 0 for all values of small x. And u is product of x and t, and capital X is identically 0, therefore u is also identically 0, and we are not interested in the 0 or trivial solution, so we will not consider the case that k equal to 0. Another possibility is, suppose k is a positive real number. So in that case we can write k equal to square of some real number which is non-zero, say mu, and our equation is x double dash minus kx equal to 0, in which we take k equal to mu square. And if I want to solve this, I will write down the auxiliary equation, which is m square minus mu square equal to 0. Therefore m square equal to mu square, and therefore m equal to plus or minus mu, and therefore solution will be some constant into e raised to mu x plus some another constant into e raised to minus mu x. These are real and distinct roots. And again, to find out a and b, we will use these two boundary conditions. X of 0 equal to 0, that means when small x equal to 0, capital X is 0. So if I take small x equal to 0, I will have 0 equal to a into e raised to 0, which is 1, plus b into e raised to 0, that is 1. So I will have a plus b equal to 0. For another condition, I will put small x equal to L and capital X equal to 0. in this solution, and I will have 0 equal to a times e raised to mu into L plus b times e raised to minus mu into L, and I have to solve these two equations. So to solve this, we can consider these two terms here. Here I have a multiplied with e raised to mu L, so I can multiply this equation by e raised to mu L. Suppose I multiply this whole equation by e raised to mu L, I will have this equation, and then I can subtract this equation from this equation. So suppose I subtract, then 0 minus 0 equal to this quantity minus this quantity, that will cancel out, and here I will have b into e raised to mu L minus b into e raised to minus mu L, and I have taken b common, so I will obtain this quantity b into e raised to mu L minus e raised to minus mu L equal to 0. And if I divide this whole quantity, or if I multiply this whole quantity by e raised to mu L, I will have 0 equal to b times e raised to 2 mu L minus 1. Okay, after multiplying this equation by e raised to mu times L, I obtain this equation. Now here mu is non-zero, L is length of the bar, so it is also non-zero. So 2 mu L will never be equal to 0, and therefore this quantity will never be equal to 1, and therefore this quantity can never be 0. So we must have b equal to 0, and if b equal to 0, from this equation we obtain a equal to 0, and if a and b both are 0, this capital X becomes 0. So if x is 0, then u is nothing but product of x and t, so therefore u is also 0, and therefore this case is also not of our interest, so we reject k positive also. And the last case is k is negative. In this case we will express k by negative of p square, where p is, say, non-zero real number. K is written as negative of p square, p is non-zero, and our equation is x double dash minus kx equal to 0, and if k is minus p square minus k is p square, so this will become x double dash plus p square x equal to 0, and auxiliary equation for this is m square plus p square equal to 0. That will give me m square equal to negative of p square, and if I replace minus 1 by I square, I will have p square times I square, and hence m equal to plus or minus p into I. So I have the complex roots with real part 0 and imaginary part p, and therefore general solution is x equal to a times cosine of px plus b times sine of px. If you recall, corresponding to the complex pair alpha plus or minus I beta, general solution is given by e raised to alpha x into cos beta x plus b times e raised to alpha x into sine beta x, and here alpha is 0, beta is p, that we have used here to write down this solution. Now I have to decide capital A and B. For that, suppose I use first condition x0 equal to 0, that is when small x equal to 0, capital X is 0. Here a into cosine of 0, that is 1, sine 0 is 0, that will give me a equal to 0. And if I take second boundary condition x of L equal to 0, then I will have capital L. If I put capital X equal to 0 and small x equal to L, I will have A is 0 now, so I am not writing A now here. I will have B times sin P into L. Here I have to write x equal to L and capital X equal to 0, and here A is 0, so I have only capital X equal to B sin Px, in which I am taking small x equal to L, so that I have B sin PL, and capital X is 0 when small x is L. Therefore we have B times sin PL equal to 0. Now A is already 0, and if B is 0, then we will have capital X equal to 0. And if capital X is 0, again U is identically 0. So we are not interested in that solution. So we must assume that B is non-zero, and because we have this product equal to 0, and if we take B non-zero, we must have sin PL equal to 0. And the values of P into L, for which sin PL is 0, are integer multiples of pi. N belongs to Z, and this will give me P equal to n pi divided by L. So I have to write this solution is x equal to B into sin Px, and P is n pi over L. So I have n pi x divided by L, and we will have infinitely many values of capital X. This B is arbitrary constant that we can adjust as, say, B equal to 1, and these solutions are different for different values of n, so we can denote them by x suffix n. So that I have written here, we obtain infinitely many solutions denoted by xn, which are functions of x only, and they are sin n pi x by L. We are not considering negative integers. For negative integers, we will obtain the same solution. The only difference is sign is negative, but we are interested in linearly independent solutions, so we are considering only positive integers. So we have obtained this in the product. We have solution in the form of product. So we have now decided values of capital X which satisfy given heat equation and boundary conditions. We have not used so far initial condition, which was ux0 equal to f of x, that is when T equal to 0, temperature is given by function of x. Now these solutions corresponds to negative value of k. We have used k equal to negative of p square, and we have obtained these solutions. So we will solve another ordinary differential equation with k equal to negative of p square. So I am taking k equal to negative of p square here, and I will solve it. So if I take k equal to negative of p square, I will have p square c square t equal to 0, and that I can easily solve because it is first order ordinary differential equation, which is separable equation. So now I have written here, we now solve equation number 7 with k equal to minus p square, and if I take k equal to minus p square, I have t dash plus p square c square t equal to 0. P is now n pi divided by L, so that we have substituted here, and c is also in the form of square, so we write p into c equal to n pi c over L and square of that quantity t equal to 0, and I denote this quantity by lambda n. Lambda n is the notation for c n pi over L, and I write my equation in this form. And again I can separate the variables. If I take this quantity on right hand side, I will have t dash equal to minus lambda n square times t, and then I consider this t on left hand side. Right hand side is minus lambda n square, and now capital T is function of t only, so we integrate both sides with respect to small t, and here we apply the formula that if we have derivative of denominator in the numerator, then it is integral is log of denominator. Therefore, integral of t dash over t with respect to t is natural logarithm of function capital T. Here we have integral with respect to t, that is we will have minus lambda n square constant. Integral of 1 with respect to t is small t, plus some constant of integration that we have adjusted as logarithm of bn. Bn is arbitrary constant. Because I am having logarithm here, I am writing my arbitrary constant as logarithm of b suffix n, because we will have infinitely many solutions for different values of n here. Therefore, we have written constant as logarithm of b suffix n. Then using the property of logarithm, we can write this as logarithm of t over bn, that is equal to minus lambda n square t, and hence t over bn is exponential of this quantity, and hence t equal to bn times e raised to minus lambda n square t. And instead of using notation t, we can write t suffix n equal to this. So we have obtained values of these functions tn, and xn is also obtained. So if we consider product of these two, and our solutions are in this form, u equal to x into t, and product of this is denoted by u suffix n. So in the next step, we write down u n x t equal to x n x times t n t. X n x was this quantity sin n pi x by l. This is x n, and t n is b n times e raised to minus lambda n square t. So these solutions satisfy the boundary conditions u0 t equal to u l t equal to 0. You can check by taking small x equal to 0 and small x equal to L, and you can verify that these solutions satisfy the boundary conditions. But to obtain the solution which satisfies initial condition also, we are interested in that solution of heat equation which satisfies boundary conditions as well as initial condition. So before using initial condition, now we know that all these un xt are the solutions of given heat equation, which is del u by del t equal to c square times del square u by del x square, and this heat equation is homogeneous and linear partial differential equation, and this un xt are solutions of this homogeneous linear partial differential equation. Therefore, we can apply superposition principle. We know that if u1, u2, u3 and so on are solutions of homogeneous and linear partial differential equation, then their sum, say sigma un n equal to 1 to infinity, is also a solution of that equation which is homogeneous and linear. So here we have these un solutions of heat equation which is homogeneous and linear. Therefore, we can use this superposition principle, and we can write that this infinite sum of those uns is also a solution of heat equation. So in the next step, I have written this summation un n equal to 1 to infinity. Here I have put their values. Now to use initial condition, I have to take t equal to 0 and u equal to fx in equation number 13. I am using initial condition for this solution. So I am writing here u equal to fx, and on this side here I am taking t equal to 0. So here I have t in the power of e. So I will have e raised to 0, that is 1, and rest of the things are independent of t, so they will remain as it is. So I have obtained that fx equal to sigma bn sin n pi x by L. And the series on the right hand side is a very familiar series. We know that this is the Fourier sine series for function small f. We can see that this function small fx is represented as the sum of sinusoidal terms, and we know that this is nothing but half range Fourier sine series for function f, which is valid in the interval 0 to L, and therefore these bn's are nothing but Fourier coefficients of this function fx, and they are given by bn equal to 2 divided by L integral 0 to L fx sin n pi x by L integral with respect to x. So here we can see, after applying superposition principle, we obtain this equation number 13, and these bn's are given by this formula 2 by L integral 0 to L fx sin n pi x by L dx, and this is our solution which satisfies given boundary conditions as well as initial conditions, where this bn is given by formula of Fourier coefficient, which is 2 by L integral from 0 to L fx multiplied with sin n pi x over L integral with respect to x. So remember this solution for the heat equation in the first case, in which we have taken the boundary conditions as that the temperature is 0 at both the ends of the given metal bar or metal rod. So we will not always apply method of separation of variables to obtain this expression. We will remember this solution, that if we have certain types of boundary and initial conditions, then solution is given by this formula. So we will remember this solution, and using that standard solution we will be able to obtain the solution of given problem which satisfies this particular type of initial and boundary conditions. So in this lecture we have obtained that if we have this type of boundary conditions and this initial condition, then solution of heat equation 1 satisfying these boundary conditions and this initial condition is given by uxt equal to sigma n equal to 1 to infinity bn sin n pi x over L exponential of negative of lambda n square times t, where lambda n is given by c n pi over L. They are called eigenvalues, and this bn is given by formula of Fourier coefficient, which is 2 by L integral from 0 to L fx multiplied with sin n pi x by L dx. It is easy to remember bn. In this integral we are writing, instead of bn we are writing fx, and we are writing this as it is, and 2 divided by L. So remember this formula for the solution of heat equation together with given boundary and initial conditions, and using this formula we will be able to find out the solution of problems related to this type of boundary conditions. So this is the first case of heat equation in which the boundary conditions are that temperature is 0 at both the endpoints. We can apply the formula derived in this case if we have this type of boundary conditions only, and initial condition we are going to consider as at t equal to 0 u is a function of x. So we will consider the problems related to this case of the solution of heat equation in upcoming lectures. Thanks for watching.